Whoa, no way. Do you know that since frogs have underdeveloped lungs, they use their skin, adapted skin, to take in oxygen and release carbon dioxide through the process of diffusion?
Wow, what a riveting fact. I really wish we could learn more about the science behind that.
What a coincidence! I was just working on a prototype to explain this to third graders like you guys. Why don't you come over to the lab and we can check it out?
Cool, alright.
Welcome back, Dustin.
What was that?
That's my computer assistant, Sahaj, the Super Artificially Intelligent Human-like Analysis Journal. This is the prototype we've been working on. Look, Nicole's working on it right now.
Wow, so how does this prototype work?
Great question. In order for a frog to breathe, it uses its skin to absorb the dissolved oxygen from the water through the process of diffusion. Diffusion occurs through a semi-permeable membrane when concentrations of two fluids are different on either side. This causes a movement from high to low concentration. The prototype was designed to simulate this process by creating a concentration gradient or difference in the amount of fog, which would cause the gas to diffuse through the frog's skin.
That's cool. So what factors influence the rate of diffusion?
Funny you should ask that. There are three major factors that play a role in the rate of diffusion: the concentration gradient, the pressure gradient, and the material type tested. The prototype here was built with the intention to test all three, but unfortunately we've come across some complications with the fog machine, so right now we've only tested the concentration gradient and the material type.
So what is the purpose of this prototype?
So the purpose of the prototype is to determine which material here visually shows the diffusion through the pipe. The prototype would be considered successful if we were able to pick a material type while computing the rate of diffusion.
Enough talk, Frogman. Let's see how the experimentation works.
Absolutely. Sahaj, pull up models and videos.
Sure thing, Dustin. Let's start from the beginning. The natural science topic this product aims to teach is the physiology of how a frog uses its skin as a means of respiration. The corresponding applied science topic is the concept of diffusion through a semi-permeable membrane, which allows the exchange of gases from an area of high concentration to an area of low concentration. On the screen is shown the 3D Creo model of the final product concept, entitled A Breath of Frog Air. The final product will consist of a fog machine connected to a clear, flexible piping system that will run through a model frog inside a display case. The skin of the model frog will be constructed with a chosen permeable material that will simulate real frog skin. Once a button is pressed, the fog machine will activate and begin to dispense an amount of fog into the piping. As time passes, the fog will be observed to diffuse through the permeable skin material. Programmed LED lights will help visually track the fog and will be color-coded to identify the fog entering the skin as oxygen and leaving the skin as carbon dioxide. There are three crucial functionalities the final product must fulfill in order to be considered successful: different concentration gradients, different pressure gradients, and different materials with varying thicknesses must all produce measurable changes in rate of diffusion. With these crucial functionalities, the product will need to teach about function and phenomena correctly and will need to address topics common to the natural and applied sciences taught at science centers and museums in order to meet the corresponding critical needs. On the screen is shown the 3D Creo model of the focused physical prototype consisting of only the fog machine, clear piping, and semi-permeable material for testing. The purpose of the prototype is to conduct simulations and testing that would lead to the selection of a permeable material for use in the final product, based on the most aesthetically appealing demonstration of diffusion. The prototype will be used to confirm that all the crucial functionalities are addressed and will allow for the calculation of the pressure difference on either side of the permeable material using Bernoulli's equation with minor losses accounted for. This equation is shown on the screen. 3 separate experiments designed based off the crucial functionalities would be conducted to evaluate the diffusion rate for a number of test materials. The first experiment will examine the relationship between concentration gradient and the rate of diffusion. For this test, fog will be injected into the inlet pipe for increasing amounts of time to simulate increasing concentration gradients on either side of the permeable material. The time it takes for the fog to diffuse through the material and to reach the pipe outlet will be recorded for each trial. 3 trials for each material will be conducted, each one with different fog concentration input. This test will be considered successful if the fog diffusion time decreases for increasing concentration, since concentration gradient is directly proportional to the rate of diffusion. Similar testing procedures will be conducted to examine the impact of both pressure gradient and material thickness on the rate of diffusion. However, for pressure gradient testing, the inlet pipe will first be secured to the fog machine dispenser to close the pipe off from atmosphere. The success criteria for both these experiments are shown on the screen. Upon analysis of the fog machine components, it was determined that pressure gradient testing could not be conducted because securing the inlet pipe to the fog dispenser would inhibit the fog from being generated. However, during concentration gradient testing, it was determined that a quantifiable pressure could be generated. Therefore, all the crucial functionalities were still addressed during experimentation. As shown on the screen, it was confirmed through testing that increasing concentration gradient does in fact increase the rate of diffusion as shown in the graph, with the upward trend line. Therefore, this testing was considered successful. Similarly, it was confirmed through testing that increasing material thickness decreases the rate of diffusion as shown in the graph with a negatively sloped trend line. Therefore, this testing was also considered successful.
Okay, but let's see it in action.
Sure thing, Dustin.
Thanks, Sahaj.
As a result of prototype testing, it was determined that 2 layers of spandex material exhibits the most visually discernible diffusion. It was also learned that for the final product, an oil-based fog machine instead of a water-based fog machine should be used to prevent water condensation within the pipe. Finally, thicker pipes should be implemented in the final design to help reduce the speed of the fog flow and to help better visualize the diffusion process. If these changes are made, the final product will meet all the needs and specifications that were initially intended.
Thanks, Sahaj. Are there any more questions?
No, thanks guys.
Great. I hope you guys enjoyed your breath of fog air.
No one told you life was gonna be this way. God's a joke, you know, love that's